Um, a universe of sets, as we defined it, is really any data of abstract objects interrelated with each other by the element relationship. So let's give an example to discuss. Uh, so for instance, it could be that we've got in a universe of sets, we've got two sets A and B, and none of them, both of them are the empty set. So none of them have any elements. So that's possible by the most general definition of a universe of sets. And also it's possible that we have a set C that has one element, set X, and the same set is also, the same X is also the unique element of another set, D. So at the moment, in the most general definition of a universe of sets, such scenarios are absolutely allowed. Now, there is not much we can do with a universe of sets which has such big flexibility. We want to put certain restrictions on a universe of sets which will allow us to make more meaningful the universe and more expressible, and it will allow us to actually implement all of mathematics thanks to those restrictions. And well, I mean, we do want the number of restrictions to be limited somewhat. We don't want to have too many of them. In the end, we will end up having actually infinitely many restrictions, but at least they can be categorized into a finite and actually quite a little number of categories. These restrictions are called axioms. And so one of the first axioms on a universe of sets is the axiom of equality of sets. And that axiom says that two sets, if they have the same contents, then they necessarily have to be the same set. So in the scenario of this example, the axiom of equality of sets says that the sets A and B, both of which have no elements, must be actually equal to each other because they have the same contents. That same contents being no contents. So A and B must then be the same set if a universe of this kind is to satisfy the axiom of equality of sets. And for the same reason, C and D must be the same set. So no two sets can exist having the same contents and these sets being different from each other. So that's what the axiom of equality of sets stipulates. And now there is a formal way of writing down that axiom that comes from that is going to employ the notation for a subset, which is a quick way of writing the axiom out. So it can be written as follows. So let's say I want to state my axiom in terms of abstract sets x and y. I want to say that x and y, if they have the same contents, then they must be the same set. So this has to apply throughout the universe to all possible x's and y's. So that's why we want to begin our formula with a universal quantifier. I'm a bit worried I'm not going to have enough space. Let me try to squeeze it in here maybe. For every x and y, something needs to happen. Okay, so how do I now express the fact that x and y have the same contents? I want to squeeze that in here. I can do that by saying that x and y are each other's subsets, right? Because to say that, so let me actually do it vertically a bit. So x is a subset of y, and on its supposed to be one line, y is a subset of x. So this is a way for me to express that x and y have the same contents. Why? Because x being a subset of y means that every element of x is also an element of y. X being a subset of y means that every element of x being a subset of y means that every element of x is also an element of y. Now, y being a subset of x means that every element of y is an element of x. And these two together with the conjunction means that x and y have the same elements, because everything in x is in y by the first part, and everything is in y that is in y is in x. So then that's the only way. The only way that can happen is if x and y have identical contents. And so now we're going to say that if that happens, right? If the contents of x and y are the same, then they must be the same set. So then x must be equal to y. So this is a formal way of writing out the axiom of equality of sets. And applied to this universe, this axiom will force A and B to be equal to each other, and it will force C and D to be equal to each other. So if they're not equal, and in this display, the way we set it up in the beginning, they don't appear to be equal because they appear at different locations. So then this universe does not satisfy this axiom. Now, once we adopt an axiom, we're going to assume it holds. So this universe is going to then fall out from those universes that we can consider where our theory is applicable, because it fails to satisfy the axiom that we adopted. Okay, so let's examine a bit more what are the consequences of this axiom for other sets in the universe. Okay, so now we figure that A and B must be the same set, and C and D must be the same set. Now what about X? The relationship between x and the other sets. Well, we don't know what contents of x is yet, so we can't say that what the relationship is. But let's say that the contents of x is, so let's say x actually consists of D and B, right? So suppose x is a set whose elements are D and B. So then the contents of x is not the same as the contents of D, right? D has only one element, x, and x has two elements, D and B. So therefore, this axiom does not force x and D to be the same, because the axiom only forces two sets to be the same when the content is the same, and in this case, the content is not the same, right? Also, the contents of x and c is not the same, and neither is the contents of x and a, right? Well, it is still true that everything in A, all the elements of A are also elements of X, simply because A does not have any elements. So A is actually a subset of X, but X is not a subset of A, because X has some elements which A does not have. So the second part here in this premise, the second part here, Y being a subset of X, well, actually, if this X is that X there, then the first part is what fails, with Y being A, right? So X is not a subset of A, and therefore X and A do not have to be the same. They only have to be the same if they were each other's subsets. And so this axiom then does not force anything on X. It doesn't force anything X to be equal to any of these other sets, but it does force A and B to be the same set and C and D to be the same set.